Hi everyone, we're going to jump from chapter 4 all the way up to chapter 7, and the chapter is titled Similarity or Similar Polygons, and it's entirely about proportional shapes or scale models, and consequently we will be using proportions quite a bit. So this first section is a complete review, I hope, of ratios and proportions, and I'm going to go fast. So what we're going to be doing in this is writing ratios, simplifying ratios, writing and solving proportions. Okay, so what is well, actually, before I talk about a ratio, quick review here of what a fraction is. A fraction is a recording style, if you will, and it means many different things, actually more than what I have listed here. But a fraction could mean pure division, a quotient. It could mean part of a whole, such as 2 slices of pizza out of the whole pizza. Probability, the odds are, 3 to 1 that someone will win the election over another person. And then finally a ratio, and that's really what we're going to focus on here, is ratios. All right, so a ratio. A ratio is, I'm zooming in here, a ratio is a comparison of one thing to another. Usually that means different units, but not always. In this picture here I have 3 red squares and 4 blue triangles, although I think your handouts are black and white, so the color distinction is lost there. But we could compare these two things. We could say, 3 squares to 4 triangles. So a ratio often is written in the form of a fraction. But notice I have units here or some kind of description. We can also write ratios, as you know, using a colon. So we could say 3 to 4. And notice the English that I just said. We would say 3 squares, I'm going to abbreviate, to 4 triangles. And getting in the habit of reading ratios this way will really help you, I think, solve some of the proportions that we are going to be using shortly. So a ratio is this comparison of one thing to another, and I think the main thing here is we're comparing 2 things. So it's really 2 things here that are being compared. And I mention that because an extended ratio over here to the right is a comparison of more than 2. So it is a comparison just like any other ratio, but it's comparing greater than 2 things or items. What's being shown here in the diagram is a comparison of 3 angles. So we've got one angle x, and then double that size of an angle here, 2x, and then triple the size of that angle, or 3x. So we can write that as an extended ratio. I'll make it a little bit bigger here. 1 to 2 to 3. That's those angles. And you can see it's you can no longer really use the fraction recording style for extended ratios. It really needs to be written out as the colon. All right. Proportions. Proportions are equal ratios. And you can see over here that we have in the diagram 3 is to 5 as 9 is to 15. And I actually want to spend the time to write that out. 3 is to 5 as 9 is to 15. Getting in the habit of reading proportions this way will really help you in the future sections that we're going to be studying. Now, we can also look at this certainly in terms of just fractions. 3/5 does equal 9/15. They are equivalent fractions. But our focus is really not on the fractions for this section. It's all about proportionality, and starting to read the English this way is really going to help. Okay, extremes and means. So we have a proportion here. Our proportion is made up of variables A, B, C, and D. It is important here to say that B cannot equal 0, nor can D equal 0, so it's important to make that distinction. But what are the extremes and what are the means? Well, we can rewrite this ratio. A is to B. Okay, I'm going to rewrite it. A is to B. I'm going to write that with the colon. A is to B as, okay, that equal sign is read as. And then we have C is to D. So go ahead and write that with the colon. C is to D. When you write the proportion out this way, horizontally, it becomes easier to see what are the means and what are the extremes. So the outside here are the extremes. They're on the outside. And the inside values, B and C, are called the means. This word mean, you know of it already. You have prior knowledge of finding the mean of a set of numbers, a data set. The mean is the same thing as the average. Well, in this chapter, we're going to be talking about a new type of mean called the geometric mean. And it's in that context that this whole, these means in the proportion are going to come into play. So I'm going to put that in the parking lot for this section, but I just wanted to plant the seed that we are going to be using this concept of means in proportion shortly. Okay, cross products. Cross products is what we use to solve proportions, solve for an unknown in proportions. Again, we've got this A is to B as C is to D. Of course, the denominators cannot be equal to 0. If this is true, if this proportion is true, then we can cross multiply. I'm going to go ahead and show it this way. We can cross multiply A times D, and on one side of the equal sign then we have AD, and we can cross multiply B times C, and that would be the other side of our equality here. So if we look at a numerical example, we've got 4 is to 10 as 6 is to 15. We can go ahead and cross multiply that. 4 times 15, and that's 60. And cross multiply the 10 times 6. Of course, that's 60. So you maintain equality. Now, cross products is not magic. It's inverse operations at work, and we're going to be taking a detailed look on that shortly. Before we do so, let's take a moment and look at some examples on how to write ratios. The two things to keep in mind in writing ratios is the order that the English is phrased. The order of the sentence is important. That's going to help determine what is the numerator and denominator. And always, if you can, try to reduce the ratio to its simplest fraction or simplest ratio that you can. Okay, let's get going here. So we've got in 2007, the Boston Red Sox baseball team won 96 games. I'm going to highlight that. Out of 162 played. Okay, write the ratio for the number of games won to the total number of games played. And I definitely have some typos here, so please correct that. I did type this fast. 1, 2, the total number of games played. Okay, so here's where the order matters. So the ratio for the games won came first in the sentence. So games won will be the numerator. And the total comes second in the sentence. So that is going to be in the denominator. So just be careful with that. 96 games won to a total of 162. And you should always simplify if you can, and we can here. So 96 and 162 are both divisible by 3. So that would be 32 wins. 254 total. And you could keep going here, I guess. One more time, I'm going to divide both sides by 2. So that would give us 16 wins. 27 total. So for every 27 games, Boston Red Sox during that year won 16. And in baseball, this is often, actually the quotient is actually found here in baseball in order to cite statistics. And so you could actually turn this over into a decimal, which would be approximately here 59 hundredths. So you could read that as their win is 59% of the time. 59 100ths. Okay, let's take a look at the next one. And I have a typo again. I'm so sorry. Okay, so we've got, there are 182 girls, this is supposed to say, in the sophomore class of 305 students. What is the ratio of girls to total students? So again, the ratio of girls came first in the sentence, so girls will be in the numerator, and total came second in the sentence, so that will be the denominator. So we have 305, and we have 182. And if I'm not mistaken, 182 girls to 305 total is as simplified as it gets. The way I would kind of look at this, just to make sure, is I would look at that number 305. When I divide that number by 5, you know it ends in a 5, so it's divisible by 5, then its factors would be 5 times 61. Both of those numbers are prime, so it's not likely that you're going to find any kind of shared number here for 182. It's definitely not divisible by 5 or 61. So that is as simple as it gets. And of course we could also turn this, actually take the quotient and turn that into a decimal as well here. All right, let's use extended ratios here in a couple of examples. Okay, so the ratio of the measures of angles in a triangle JHK is 2 to 3 to 4. That's how we would read that, 2 to 3 to 4. Find the measure of the angles. Well, it's not a bad idea to always draw some kind of diagram. So 2 to 3 to 4, we could say we're not sure what those angles are. We could do a lot of guessing and checking, but the way to do it algebraically very quickly is we can say, we don't know what the angles are, but I could say one angle is 2x, the next angle being 3x to 4x. Now I haven't changed those ratios at all. 2x divided by 3x is still 2 to 3. 3x divided by 4x is still 3 to 4. So we haven't changed anything by adding that unknown. We're still in that same ratio. I'm going to go ahead and, I don't know, I just like to fill in my picture here. So we've got 3 angles, and we know by the triangle angle sum, they're going to sum to 180. So we could say 2x plus 3x, that's an x, plus 4x equals 180. And we have 9x equals 180, so x equals 20. And once you solve for that unknown, you're going to find the angles. So 2 times 20 here, 2x is going to give us 40 degrees. 4 times 20 is 80 degrees. And 3 times 20 is 60 degrees. And just sum them up. Make sure you're summing to 180. 40 plus 60, of course, is 100 plus 80. So everything checks out. You should always check your answers. All right, the ratio of the sides of a triangle are 8 to 15 to 17, and the perimeter of this triangle is 480 inches. So let's take a look at that. So we've got triangle again, and we've got this ratio. I don't know what this thing is here. 8 to 15 to 17. Again, we don't know what those sides are. We introduce an unknown. Perimeter, as you know, is the sum of the sides. So we know that our perimeter is 8x plus 15x plus 17x. And we know that the perimeter that's been given to us here is 480. So I'm going to substitute that in. And 8x plus 15x plus 17x is 40x. And so x is 1, that would be 8, so that would be 12. And we can substitute in x equals 12 into each side, and we should to check that. 8 times 12 is 96. And let's see, 15 times 12 is 100. Whoops, I don't want to do that. Is 180. And 17 times 12 is 204. So sum these all up, and I get 480, so everything checks out. This is a 0, by the way. It's a messy 0. Let me fix that. So 480 inches, everything's perfect. Okay, great. Little practice solving proportions. I'm going to zoom in here. So we have a first proportion, 1:2, as 28 is to x, and we can just use our cross products. 1 times x is x, and 2 times 28 is 56. All right, taking a look over here, we've got 3 is to 18 2/10, as 9 is to y. We're going to cross multiply. We have 3y equals, and I'm going to use my calculator for that one in the interest of time, 10.2 times 9, and we get 163 8/10. And y equals 5. That would be 4, and I have one more, so that would be 6. 54 6/10. And finally, this should all be reviewed for you. When we cross multiply here, and I have kind of an algebraic expression up here in the numerator, make sure that you know that 4 is multiplying that entire sum. So that would be 4 times the whole sum. I need to put that sum in parentheses. And 8 times 5. So 8x plus 12 equals 40. I'm going to subtract 12 from both sides, and that would be 28, correct? Yeah. And x equals 3, and a remainder of 4/8. So you can leave it as 3.5, or I guess 3 5/10, if you like decimals. All right, the last thing I want to do is go more into algebraic proof here regarding the cross products, as well as some other properties. So let's take a look at the original cross product here. Why does it work? Well, I'm going to start with a proof here. We know that the cross product says that if A is to B as C is to D, and of course the denominators are not zeros, then we know that AD equals CB. That's the cross product. So why is that true? Well, I'm going to attempt to prove that right here. I'm going to erase this just to give me some room. A is to B as C is to D? Well, A here is being divided by B. How do we undo division? We undo division with multiplication. So I'm going to multiply that by B. To undo that division, inverse operation, whatever I do on one side of an equal sign, I got to do exactly the same thing on the other. So what happens here is this B divided by itself would reduce out to 1. Now over here on the right side, C is being divided by D. How do I undo that? I undo division with multiplication. Whatever I do on one side of the equal sign, I have to do on the other. So that has the effect of D being divided by itself. And so what you have left is the product of A and D and the product of C and B, and they are equal to each other. So hopefully you see that cross products are not, math magic. This is just inverse operations, same old inverse operations we use every day when we're solving equations. Okay, well there are many other properties of proportions, but I'm going to highlight 3 of them. The first is called the reciprocal property. The second is called the exchange property, and the third is property of 1. And I want to go through a proof for each one of them. And we're going to start out the proofs with our original proportion as we always have. So we're going to start out here with A is to B as C is to D. Of course, the denominators cannot be 0. Okay, so I want to prove that I can actually flip the numerator and denominator. Now put B over A, and that's going to equal the reciprocal over here, D over C. So I want to prove that this is also true, and I'm going to do it by going right back here to my inverse operations. So A is to B, well, I'm going to undo that division with multiplication. And of course these are going to reduce to 1. C is to D, I'm going to undo that with multiplication. Whatever I do on one side, I have to do on the other. D divided by itself reduces to 1. So let's go ahead and start out here with our cross products. A times D is left over here on the left equals CB. Fair enough. Now I want to prove that B divided by A equals D divided by C. Okay, well I have B in the numerator over here, so let me divide that side by A, because I want B over A. So I'm going to go ahead and divide this side by A. Whatever I do on one side, I have to do exactly the same thing on the other. And you can see that A divided by itself reduces out. So I have D equals the product of CB divided by A. Well, what I'm trying to prove is D divided by C, so I'm going to go ahead and divide the left by C, and whatever I do on one side of the equal sign, I have to do exactly the same thing on the other. And of course, anything divided by itself reduces to 1. So right now, what I have left is I have D divided by C equals B divided by A. And with the symmetric property, of course, we can flip that around. B divided by A equals D divided by C. So we've proved this property of proportion, the reciprocal property. All right, let's try proving the exchange property. The exchange property, I'm going to go back here. If you can take a look at the difference here, D divided by B. Well, what happened here? It looks like from our original proportion, D is moved up and replaced positions with A, and A is moved down. So that's the difference between here and here. Now let's prove it. We're going to prove it right back with our cross products. So we have A divided by B equals C divided by D. We're going to undo this division of B with multiplication, and we're going to undo this division over here of D with multiplication. And whatever I do on one side, I can always do, well, I not only can, but I have to do the same thing on the other side. And we end up with simplification. So we're right back to A times D equals C times B. This is our cross products right here. We should probably point that out. Okay, so what are we trying to achieve? We're trying to replace or exchange the D and the A. So I have D already over here in the numerator, and I want to get B down here in the denominator. So I'm going to divide by B, and whatever I do on one side, I got to do on the other. These cancel. And then I have C in the numerator, and I want A in the denominator. So I'm going to do the same thing. I'm going to divide by A, and so these cancel. And there you have it. We've proved that D is to B as C is to A. And so we've proven the exchange property. And finally, we have the property of 1. The property of 1 states that if A is to B as C is to D, then this is true. So the sum of A and B over B equals the sum of C and D over D. So how can we prove this? Well, this one's easier, and we're not going to start with the cross products. We've got if A is to B. Oh, I don't like the placement of that. If A is to B as C is to D, then the property of 1 says we can add 1 to both sides. In fact, we could add any number to both sides as long as we do the same. And if I wanted to add the number 1 to A over B, then I'm going to replace 1, or rewrite 1, if you will, with B over B. That is 1. And over here, C over D plus D over D. Why am I doing that? Because to add fractions, I need a common denominator. So A plus B, the numerators here, A plus B over B equals C plus D over D. And that's what we were trying to prove, the property of 1. Okay, thanks for listening. Please subscribe.